Okay, is everybody in the room here undergraduate? Yeah. So this week, masters split off. Masters don't even get to see this week. And then we go on our applied diffusion kinetic section. So you had Rakesh's exam on Thursday. You okay? A little bit nicer than Jason's exam? Yeah? It's the usual thing. Okay. So there's around about 23% of you here that probably should be here for this class. Okay, so low attendance. I will take a roll every now and then in this class. It doesn't really mean anything, but what I do with that data is just see what the grades are of the students that actually rock up to a lecture and those that stay home and get an education like the bedside table. Historically, and the gap's actually getting bigger, we do see this bimodal distribution of grades. Okay? Usually you've got the core 25 to 35 students that actually show up to lectures. Some of them live on campus, so it's nice and convenient for them. Some of them are close by. And the others just couldn't be asked doing it. All right? But yeah, basically the gap in 2017 when online lectures first came online and the culture of not having to come to lectures and relying on digital recordings began. We saw about a 12.5%, 13% difference in grades of students that showed up compared to those that didn't, on average. That's almost at about 17.5% this year. All right, so it's getting further and further apart. So by showing up to a lecture, listening to your lecturers crap on about stories and give you actual lectures, you're probably getting a little bit more out of it than what you get out of lecture recordings. We know the recordings aren't great. UNSW is trying to fix that as best we can. But as always, the recommendation of any lecturer is going to be actually to show up. Right? Who here hates this course so far? It's been pretty tough, yeah? It is a tough course. It's essentially kind of the first course where you've really got to think about something in science and really apply yourself and learn. Okay? It's got some tough concepts, right? It is kind of this fusion of a couple of different courses from the past, right? Diffusion and kinetics, the course that you're taking now, is actually, or was once upon a time, two separate courses. Physical chemistry and diffusion mechanisms, or more affectionately known by the students, confusion mechanisms. Okay? It's tough. It is the most failed course in material science. Okay? And it kind of causes this gap. You're going from some cool, nice, easy basic chemistry, mathematics, physics type courses, all right, that you've got a bit of a background on, into something that's very material science based and focused, and it's not so easy. And a lot of students, particularly second year students, will fail this course. All right? It was much higher fail rate when Nagy was teaching it than it is now. The average grade for the course over the last 5 years was 59%. This is before I started teaching it. At the moment, the number of students that would fail it are about 5 to 8 annually. Okay. Now, out of a cohort of 120, 180, if you include the master's students, that's not too bad, really, from where I stand. And again, as I mentioned, traditionally students gave the name of this course was Confusion Mechanisms. Have a look at this guy here. Alright. So once upon a time, as I mentioned, this course was 2 different courses. Physical chemistry, run by the chemistry department. This still kind of exists. This is why Jason from chemistry took the first part of the course, kinetics. Yeah. It was also the other half, which is diffusion, which was traditionally taught by material science. Okay? So this particular guy here, who did this course back in, must have been 1999, maybe 2000. Okay? You can see here, even back then, it's a pretty tough course. Okay? Just passing. And now here I am teaching it to you. Alright? And it is. It's something that's very specific to materials and chemistry that we've got to work hard to actually learn and pick up concepts. Alright? How this thing's laid out. Now, a lot of people whinge and complain, students whinge and complain, that you've got a fairly early exam for Jason's part. Alright, week 3, did we push it to week 4? We tried, but we couldn't. We've actually got a lot of restrictions where we're allowed to put assessments and things. This is University Central. We've got our hands tied as to what we can do with things like that. And because we have the master's students tied into this course, we have to get those first 2 blocks of kinetics and diffusion fundamentals done by, used to be weeks 1 to 6 when we were in the session system. Now we've got to get it done by weeks 1 to 5. Okay? So Jason's part happens very, very early, and you're doing your 6 hours a week on that, and then doing the exam. Rakesh's part have to be completed by the end of week 5. Once upon a time, it was even more messed up than what it is now. We had 2 lecturers from chemistry teaching kinetics and reaction engineering in the one course, and you'd learn about kinetics and reaction engineering for 2 hours on Monday, and then you'd have to, switch your brain up and do diffusion on Thursday. Okay, so they were teaching them in parallel, which is a little bit silly. Okay, too much overload on you guys. You can't learn 3 different topics at one time. All right, so when I took over the course, we went, righto, let's get rid of this lecturer. We don't need that lecturer anymore. That's just silly. We're going to block this up into kinetics, diffusion fundamentals, applied diffusion kinetics. You also had 2 exams at the end of the year for the same course. A little bit silly. So what we did was block it up like this. Kinetics, exam. Okay? So learning on one topic, exam on one topic, and so on. Is a little bit challenging. I think next year we're actually going to be splitting the master's students off. I think we have to buy another lecturer to basically teach this course for the master's students and the undergraduate students in 2 separate batches, which gives us a little bit more flexibility with our timetable and labs and things like that. Alright, so hopefully that makes the 20 or so of you that have showed up today feel a little bit better. We'll see. Typically Rakesh's exam, students get the highest score, only by about 1% or 2 compared to my exam. And Jason's exam is very, very hard. There's also a reason for this as well, that you find Jason's part very difficult. Right? Material science students don't have to do chemistry 1B anymore. Once upon a time they did. Okay? And with the background knowledge of chemistry 1B, probably would have found the kinetics part much, much easier. Right? So sometimes we've got advanced science students sitting in this room. They usually get 22 out of 25, 23 out of 25 because they've done chemistry 1B. Again, you're not really getting the degree that you did once upon a time. We're having to keep cutting content all the time as your degrees are truncated. Anyway, so that's just a little bit of information. Okay, so the section that I'm going to be talking about is more on applied diffusion kinetics. Okay, so Jason's taught you some hardcore things about kinetics, reaction rate constants, okay, the types of things that can affect kinetics, catalysts, stuff like that. Rakesh has kind of taught you a lot of formulas, I guess, about the fundamentals of diffusion. Okay, what diffusion is, how it works. And you've done some number crunching in his teaching you has very few equations. There's a little bit in the nucleation and growth section, but I'm not expecting you to remember equations. I'm not examining you on equations or calculation. I'm going to examine you on learning stuff. All right? What does this do? Why does it do it? How does kinetics and diffusion affect that? So my exam's a written exam. Don't even need a calculator. All right. So, just in case you didn't show up to the first 5 weeks, we're going to have a little bit of a chat about kinetics and diffusion on their own, and then we're going to start blending them together and some of the things that we observe every day. So, I'll pose a question to the class that's very spread out in the lecture theatre. What do we think of, or what is chemical kinetics? What is it? Definition. Give me a dictionary. Whatever. Yeah.
Reaction rates.
Yeah, reaction rates. This is a good start. What are we measuring?
Time.
Time is a very important part. Okay. And what's our change over time? Yeah. Of. Yep. So that's pretty much it. Good. Some of you are awake in that section. So chemical kinetics is concerned with measuring, studying, and defining the rates of chemical reactions. Okay? How fast does a reaction proceed and why? The rate of a chemical reaction is defined as the rate of change of the concentration of one of its components, either a reactant or a product. Pretty straightforward, yeah? So, okay, in chemistry this is pretty easy, I suppose. Okay? You've got chemical A, okay? You do something to chemical A, it reacts, transforms, and you've got a concentration of chemical B. It's not always about chemicals. It can be change of state, okay? It can be all kinds of different things, kinetics. Can anyone think of any examples, either from Rakesh's section or Jason's section, where reaction rate kinetics can be observed and are actually critical to an application? Yeah.
Maybe some examples like batteries where you use a gas and you need a catalyst in support. There's some reactions that just can't happen or happen too slowly without catalyst.
Without catalyst, so we need a surface for a particular ion exchange to occur, and a lot of battery or fuel cells. That's a good example. Any others? Some very basic ones that we don't really think about every day. Anyone think of any others? Huh? So, when we're talking about kinetics, right, reaction rates range from things that are almost instantaneous. Okay? We don't even realize that a reaction is occurring, or an exchange of ions or electrons. The example is just an explosion. Okay? Very, very fast. Two other types of reactions that are just unnoticeably slow, as in something like corrosion. Yeah? So these are kind of everyday applications. Turn the key in your car, if you are still driving your car with an internal combustion engine. There's a reaction going on in that combustion chamber. It's almost instantaneous. Adiabatic. Okay? However, over time, you leave that car out in the rain, particularly near the coast, it's gradually going to transform to its lower energy state, which is typically iron oxide or rust. Yeah? So all kinds of different things. Okay? Here's an example. Nuclear fission, chain reactions. Okay? Typically, these can be very, very fast. Okay? Chain reaction, the breakdown of non-stable radioactive material. Right. They can also be very, very slow. Radioactive decay can happen over hundreds and hundreds of years. That's just one example. Combustion, very, very simple reaction, isn't it? Usually we've got something that's carbon-based, carbon-hydrogen based, okay? And we burn it in air, react it with oxygen. A little bit of heat from a flame there, okay? Combustion can be very, very fast, as in the internal combustion engine where we've got optimized parameters for high-speed combustion, Okay, we've got a vaporized fuel source, we've got pressure, we have an ignition source, and pop. Bang. Yeah. Typical car engine at idle will idle at 800, 900 RPM. That's a lot of bangs and pops per second, yeah? Motorcycles go up to 22,000 RPM. That's a lot more bangs and pops per second. So very, very fast kinetics. All right, and then we can think about our slow combustion fireplaces. Some people might have a fireplace at home. Throw a lump of hardwood in there overnight. Don't expose it to too much oxygen, okay? Blows your flue. And that lump of hardwood can burn overnight, okay? Could be still smouldering there in 8 hours' time when you wake up in the morning. Biological reactions. What are you doing now? Hopefully breathing. Yeah? The Krebs cycle. Okay? What is it? It's an exchange of oxygen, transferring it to carbon dioxide. Yeah? So biokinetics. What happens if you decide to do 20 laps of this lecture theatre? Heart rate goes up, burning more oxygen, much more exchange, fraction rate of kinetics go up. I'd probably call an ambulance because there's something wrong with you. Yeah? Neurokinetics, electronic signals up and down your spine. Yeah? Almost instantaneous, but there's a lag there. In plants, photosynthesis. Okay. These are all reactions. They all occur with a specific reaction rate. And we're changing the chemistry of our products and our reactions to produce something. A plant will grow. A plant will expel oxygen. Here's the example that we already had. Right? Chemical fuel cells, batteries, water splitting technology. Okay? They are all chemical reactions. Okay? Often these things for use in technology need fast kinetics. Right? We need to be able to discharge or recharge our energy storage devices as fast as we can. Otherwise they're seemingly useless to us. Yeah? So the auto industry is kind of going through this change at the moment. How do we store our fuel? How do we recharge and discharge our fuels or our energy sources more quickly? Yeah? As materials engineers or even chemical engineers, as you move forward, these might be things that actually climb on your critical list when you're designing things. Some other more material science-based processes. Polymerization. Yeah? Hopefully we all know how polymerization works. Okay? It's a chemical reaction or an interaction where we're trying to join up our chains of hydrocarbons to form a polymer. Right. And there's typically some other things we add to polymers to speed up that reaction. Another one was changes of state, probably something that you don't really think about too much as a kinetics reaction. All right. A change from liquid to solid. Change from solid to solid. Okay. Particularly in metallurgy, that's a big one. Change from one phase to another phase. Yeah? So these are all things that we can put under our broad heading of kinetics. Okay? It's not just chemical reactions. All right. So we've had a few examples there. Let's ask a question. What might affect, alter, or influence reaction rate kinetics? There's some pretty simple ones there. What changes the rate? Gas.
Temperature?
Yeah, so probably first and foremost is temperature. Increase the temperature, most of the time, we're going to push that reaction rate forward, yeah? That reaction direction. What's some others? Pressure, okay, yeah, all right. Some basic chemistry stuff there. What are some other things that might increase it? Catalysts, yep. So that was one that we've had mentioned already this morning, catalysts. Something else that might affect reaction rate kinetics. Yeah, so basic thermodynamics, key thermodynamics. What are our underlying driving forces for the reaction to occur? Okay, adding catalysts can alter those through nucleation and other events. So yeah, activation energy is a key part. Otherwise, the nucleation of an event, start of the event. Yep.
The concentration or the surface area of the reaction?
Yeah, so concentration. Obviously, the fusion is a gradient process. We're trying to even things up, find equilibrium. So if we've got an overconcentration of a reactant or a product, that can shift our equilibrium, okay, and the driving force of our reaction, the rate of our reaction. Surface area is also something else if we are relying on the surface to start that reaction. Even surface geometry and shape can affect that reaction. There's one other big one that I was hoping someone might get. It's physical. It's got nothing really to do with chemistry. What can we do if we've got component A and component B? We tip them into our beaker or test tube. What's something we can do to help speed up that reaction? We heat it, but we've already spoken about temperature there. Stir. Agitation. Okay? Convective currents, things like that can also speed up reaction rates. Yeah? So what have we got? Temperature and thermodynamics. Yep, tick. Good. Catalysts and enzymes. Yeah, these are other things that we can use to speed up our reactions. Our body relies on enzymes for reactions to even occur. Inoculants and substrates, that's something we didn't mention. So we spoke about surface area as a possible thing to speed up a reaction. The geometry of that surface area, that's kind of related. Right? So having a substrate present might allow for the interchange or change of an ion or an electron to occur more quickly. Okay? So providing a site for a reaction to occur more quickly. Does anyone know what an inoculant is?
Sorry, I was just going to ask, could you explain the substrates again?
So it's very broad, and I think the answer I'm going to give you is probably maybe too broad. But having a substrate or a surface, same thing. Okay, that substrate may allow chemically or topographically, might give us a site where the activation energy for an event is lowered. And when we lower the activation energy for a reaction to occur, it's going to occur more quickly or more easily. We'll get onto that. I think we've got a slide that covers this in the second lecture, which I'm hoping to get to today. Inoculants, anyone? So inoculant is something that we might add to our material. It behaves like a catalyst of sorts. It's a solid. There's a condition involved with the surface of an inoculant that makes the reaction occur more quickly. In metallurgy, an inoculant is basically a crystal. The lattice parameter of that crystal matches that of the product on a certain plane and allows it to grow much more easily. It's a surface energy effect. What about this one? Diffusion. Okay? Getting the atoms from site A to site B where the reaction is going to occur is also very important. Diffusion involves distance and time, yeah? Affects our reaction rate constants. Okay, and as we mentioned before, environmental effects, currents, convection, stirring, agitation. All right. Can also speed up our reaction rates. Okay, so we don't dwell on it too much. What is diffusion? Okay, so diffusion is the movement of a chemical species, be it an atom, a molecule, or an ion, from an area of higher concentration to an area of lower concentration, a concentration gradient. Okay. So diffusion is a result of the kinetic properties of particles and matter. Over time, the particles will mix until they are evenly distributed. Diffusion may also be thought of as movement of particles down a concentration gradient. All right, so hopefully you've picked up on that from Rakesh's section. Let's give some examples of diffusion, huh? So you've probably had some exam questions, hopefully, that you remember on diffusion. What's some examples of diffusion? Osmosis. Yes. Highly technical word, yes. Osmosis is an example. What's osmosis?
The water molecules diffusion from the high concentration to the lower.
Okay, sure.
Yeah.
Through a membrane, yeah, sure. Okay, any others? Think basic, every day. Oxidation. Yeah, to an extent. Okay. There is a penetration penetration event, I suppose it does occur under ongoing oxidation, but usually it's immediately at a surface. You still need to diffuse the molecule from the environment to the surface. Yeah? Perfume. Take one of my good examples. Yeah, okay. Yes, any others before we keep going? Sugar and water, yeah. Dissolving your sugar in your tea or your water or something like that. It then distributes. Okay. Diffusion in gases. Yeah, somebody got the perfume one. Okay. How are we for time? Let's have a look. We have no internet. Awesome. All right. So a great part about internet security in university, I get my laptop, walk 5 meters from my office to here, and I have no internet anymore. And you have no images whatsoever. All right. So typically I would click on that link and it'd go to an ad for Chanel No. 5. It's got Nicole Kidman in it and that other guy out of Moulin Rouge. Okay, and it's kind of, the key takeaway is that it sounds a bit weird and creepy, but you can kind of smell her across the room. All right. So I typically play that. If we had a bit more time, I would do it in interpretive dance, but we better not. All right, now, so that's one example, yeah? The smell of perfume diffusion across a room, okay, from point A to point B. And I think Rakesh gives the example, I think, of exhaust fumes in a garage or something like that. He might have given it in an exam or in a tutorial, okay? Gas is diffusing from one point to another. I would then get really kind of funny and try and use the baked beans, okay, as another example, okay? And here I show a section out of a real old-time movie, Blazing Saddles, when it wasn't politically incorrect to use farting as an example of diffusion, okay, across the space. All right, what we might do, just quickly, because I really want to get these things working again, we'll take a 5-minute break and we'll see if we can get the bloody internet running, because they're kind of critical to your learning. Okay, so just take some time out for a sec.
pizza with more fresh ingredients, a Don Pizza Checker quality guarantee, and any pizza from $15 delivered. With Domino's, everyone's happy.
Very old school humour.
How about some more beans, Mr. Taggart? I'd say you've had enough. I understand there's a new sheriff in town. Who wants to kill him?
Okay, so old school movie trailer. Now, we've resorted to using my own personal internet. Okay. What about diffusions in liquids? What are some examples? Okay, so here's an example here where we've got two different levels of temperature. Okay, we can see the diffusion of our liquid dyes in the hot sample of liquid, moving much more quickly than that in the cold one. Partly due to convective currents as well, yeah? Even after 30 minutes, we still haven't got complete diffusion in our cold sample. Okay, but after an hour, okay, we're distributed evenly enough. Okay, the other example is tea. Okay, many of you actually drink tea, right? But we've got the dispersion of a couple of things here, haven't we? We've got the obvious colour change. Okay, a cup of tea, green tea, black tea. Right. We've also got the distribution of other things, the molecules that impose flavour. Yeah. What about diffusion in solids? We've got any examples of diffusion in solids? Rakesh probably had one there at least. Did Rakesh speak about carburization? Yeah? Carbon diffusing through a solid. Right. Here's an example I like to use. Right. The deflation of a balloon. Right. A helium balloon, floating balloon. Small light atoms like helium can diffuse through the tiny pores or structural gaps in rubbers and plastics and even metals. Right. And similarly, air, nitrogen, oxygen can diffuse in. Okay. So this is often the reason that our balloons stop floating, our helium balloons. Okay. Diffusion of helium out, and often we can have diffusion of other elements in. Another example, US pennies. All right. So pennies from the USA, or 1 cent piece, yeah, they're made of zinc and they're plated with copper. So typically, this is what they would look like on the street. When we actually heat them, what happens is the zinc diffuses into the copper, forms a metallic solid solution. All right. So when we add zinc to copper, what do we typically call it? A brass. Okay. So as that zinc diffuses into the copper, it changes color. It goes yellow, like a yellow brass. If we continue this reaction even further, more and more zinc diffusing to the surface, okay, so matching that concentration gradient, we end up with a silver-coloured coin. We actually start to form copper zinc intermetallics that are silver in colour. Okay, so there's our phase diagram there. We start off over here. All right. As we add zinc to the system, we go from the pink-red colour of copper, okay, to the yellow-gold colours of brasses. And once we get into this region over here, we turn silver-grey. Another example of diffusion in solids, carburization and nitriding of steels, case hardening. Okay, often our steels, mild steels, are very, very soft and tough and durable, which is what we want. But those steels are clashing with other steel components or sliding, so we want to make the surface very hard. How do we do that? We actually add carbon or nitrogen to that steel. Okay, we can change the structure of that steel to something much, much harder. Okay, requires quite a bit of temperature, and typically we'd use a carbon bed or methane, okay, to get our carbon to diffuse into the steel. All right. So as we increase the carbon content, we start to form harder intermetallic compounds will form, and we also get interstitial carbon in our structure, making the steel stronger and harder at the surface. Okay, so for lecture set 1, just a quick revision of what had gone on in the course with some examples. Hopefully we've learned a little bit today already, okay, about how chemical kinetics is used in other things other than just chemical reactions that we see every day. Okay, it's concerned with how fast a reaction proceeds and why it might proceed quickly, the rate that it proceeds. And then diffusion is just the movement of chemical species, okay, from an area of high concentration to an area of lower concentration. Right. Something that hopefully you'll learn as we go through the course is most of these aspects are the underpinnings of all material science-based mechanisms. Okay. So all the things that metallurgists, ceramicists, polymer scientists might be studying in the future, okay, are all highly, heavily, probably mostly defined by diffusion kinetics. They're trying to change our materials into something better, faster, lighter, stronger, whatever else. Okay. And that change is often associated with diffusion and kinetics. Change from one phase to another, something like that. All right. So that's typically what I'd give as a quick introduction. Okay. What we're going to do now is move on to the next part of our lecture set, which is an introduction to nucleation and growth. Okay, so again, this is kinetics and diffusion at play. Right. All right, so interactive. Can anyone here define nucleation? What is nucleation? What does that mean? What does that word mean? Oh, you answered too many. This one else ago. Anyone? I'll come back to you for that. Nucleation. All right, you're on. Nucleation.
When water freezes into ice, it doesn't happen everywhere at once. It happens in little small spots. So small spots. Then forming is nucleation and then growing.
Yeah. So nucleation is basically the starting point of a change. Yeah. Phase change or starting point of a reaction. Yeah. So nucleation is the point where something goes from one phase to another. This doesn't happen everywhere instantly. It will often happen at a specific site because that site will be of lower activation energy than another. Okay? So nucleation is the first step in the formation of either a new thermodynamic phase or a new structure via self-assembly or self-organisation. Nucleation is typically defined to be the process that determines how long an observer has to wait before the new phase or self-organised structure appears. Hopefully you might start to see that any process can be a multiple-step process. Right? The first step is getting this nucleation event to occur. There has to be a driving force for the nucleation event. Okay? Once that occurs, then our reaction can proceed. So the kinetics associated with that nucleation event, the thermodynamics associated with it, would be completely different to how that reaction would then proceed. Does anybody know what determines nucleation rates? It can be all manner of things. It usually is having a specific site where the activation energy for that nucleation event to occur is overcome so the reaction can start. So nucleation kinetics, the rate of the transformation onset is generally determined by the local thermodynamic driving force and the ability of transformation constituents to transport themselves to a new site or orientation. This part of the step is usually diffusion based. So local thermodynamic driving force, there has to be something going on in a specific location where our reaction is taking place for nucleation, for that reaction to start. It could be something on a surface, right? You might have an impurity on a surface. You might have an impurity in your alloy melt or your chemical melt. And that impurity locally provides a site of lower activation energy for that reaction to start. Right? It could be the edges of your beaker, something like that. Yeah.
I'm getting a bit confused when you say thermodynamic driving force. Thinking about thermodynamics, it's like against entropy. Like if you've got water going into ice, things want to be more disordered. So how do you get over that want to be more disordered?
No. Things don't want to be more disordered, they want to be more ordered. Because by decreasing entropy, the free energy is getting lower. Because it's a negative sign in front of our negative T delta S.
Right.
Okay, so we're trying to actually create a more ordered structure. But what I'm talking about here in terms of our free energy or our driving force, okay, is for your reaction to proceed in a completely homogeneous way, it actually takes a lot of energy for the structure to locally overcome the barrier to nucleation. Okay. Once it is overcome, and it happens stochastically anywhere in the melt, which is probably what you were talking about a little bit before, the reaction will proceed quite easily. Okay. By having an impurity or a surface or an asperity on a surface, okay, the localized energy, activation energy for nucleation can be lowered. Sometimes it can be higher. Right? But if it is lowered, then that's going to be the site where nucleation is going to start and then proceed to growth. All right. So naturally, the number of nucleation sites available to a forward reaction or transformation is a predefining step as to how fast an overall reaction can proceed to completion. So nucleation is followed by growth, which is another rate-defining process in the completion of a transformation. Right. So nucleation and growth are almost independent of one another. All right, so we've spoken a little bit about them. What are some other factors that might influence nucleation? We've said some. Impurities. Surface. The surface can be considered as a catalyst, yeah, to start that event. Anyone think of any others? Yeah, so a grain boundary in a material, okay, often we get precipitation at a grain boundary, focus migration happens at a grain boundary, okay, and that's again associated with energy. The structure at the grain boundary is actually disordered. We've got two crystal lattices, different orientations butting into one another. Okay, where they join, the atoms have to try and bond as best they can over that grain boundary. It's a high energy location. Right, material, all materials, natural materials want to reduce their energy. Right. So a high energy site is a good place for nucleation to occur, so the material can reduce its structural energy. Okay, so what determines nucleation kinetics? So nucleation is usually a stochastic or random process. So even in two identical systems, nucleation will occur at different times in a perfect world. Okay? Nucleation generally occurs under two condition types: homogeneous nucleation and heterogeneous nucleation. Does anybody know the difference? I talked about it a little bit earlier. I mentioned homogeneous nucleation. What would homogeneous nucleation be?
Would it be evenly spread out?
Yeah, spread out. Yeah, so non-localized. So what would heterogeneous be on the other hand? A localized type of nucleation. Yeah. All right. So homogeneous nucleation. Nucleation occurs within the body of the phase, the material. All right. And what happens is we have microscopic fluctuations of the nucleating phase appearing and decaying, okay, in equilibrium. So, for example, going from solid to liquid, right? Randomly in our, well, liquid to solid, randomly in our water we would have crystallites. Okay, only a few atoms in size starting to order, and then they would disappear in disorder. Okay, because if they don't reach a critical size to grow, they have to disappear. And we'll get onto this a little bit more detail next week. All right. Well, what happens is these microscopic fluctuations of the nucleating phase, they appear and disappear continuously until we get an unusually large, and we'll say random, large fluctuation of the new nucleating phase, which is large enough to overcome the nucleation energy barrier, right? Where it's more favourable to actually grow rather than decay. So we can actually describe this process using classic nucleation theory, which we'll do next week. Okay. But yeah, there's an energy barrier for nucleation. Right. So little crystallites will appear and disappear as the material's in equilibrium, approaching, say, a solidification temperature. Right. Until some point, one of those sites will be big enough, or you might have two nucleation sites very close together, creating a localized energy. They might combine. And then we hit our critical size, okay, for nucleation to occur. Heterogeneous nucleation. Okay, so nucleation is very sensitive to impurities or foreign bodies in contact with our system. Because what those bodies will do, or often will do, is create a low energy site or interface for nucleation to occur. Okay, and the examples here are if we have a chemical contaminant in our liquid or our solid or something like that, a solid impurity particle, or even just the containment vessel wall. Okay, what are we containing our reaction in? The presence of this surface can lower the local energy barrier for nucleation and hence determine the nucleation rate. Okay. Heterogeneous nucleation is by far the most common. Okay. Homogeneous nucleation, you have to have some very, very clean conditions. Often the containing vessel is going to be the same as the material that you're actually nucleating, right? So that we don't provide any nucleation sites, right? Or the vessel has to be a known poison to nucleation of that system to get homogeneous nucleation. Most of the time in industry or in science, right, we're dealing with something that's not quite perfect conditions. Okay? Often things like our alloys will have to have impurities in them. We rely on them for strengthening and things like that. So they provide sites for nucleation, crystal growth, solidification, things like that. Sometimes we doctor the system to have heterogeneous nucleus in there to make solidification faster, or make it more evenly distributed. Okay? So we add inoculants to our alloys so that we get a finer grain size, which gives us better properties. Okay, so these are things that we can, sometimes we don't have control over them, sometimes we can engineer them into our system and take advantage of them. What we might do is, typically I'd have a 10-minute break between lecture sets on the hour. Right? So we'll take 5 minutes, we have a little bit of an internet disruption. So you guys can have a little bit of a recharge and regather. And then we'll have a look at some examples of nucleation and growth. Just basic examples. Okay? Okay. Just going to pass around a sheet of paper. Just want to chuck your name and student number on it. That'd be great. And again, doesn't mean anything, doesn't affect your grades. I'm just interested to know who's getting the learning. Who here sat Maths 2003 in T1? Yeah? How many of you actually came to the lecture I gave on atom probe tomography? I think you did. I don't know about you guys. I don't know. So I gave a lecture over in Law Theatre, which is a massive theatre. Yeah? And of the 120 so students enrolled, I think I had 6 show up for a Friday lecture. That question was in the exam. 6 people got it. Yeah? It does. It pays to show up, even if it is a Friday, 11 till 1 or whatever. It's the most boring thing you think it's going to be. Pays to rock up. Okay. Alright, get started again, guys. Alright, so one typical example of nucleation and growth, alright, is condensation. And that's just the change of a physical state from the gas phase into the liquid phase. Yeah? So condensation commonly occurs when a vapor is cooled or compressed to its saturation limit. Okay, so this is when the molecular density of the gas phase reaches its maximum threshold. Condensation is nucleated by the formation of atomic or molecular clusters of that species within its gaseous volume. So just like a raindrop forming within clouds, yeah? So it's nucleated at a site locally, then continues to grow to a size where it can fall as rain, right? Or contact between a gaseous phase and a liquid or solid surface. Right, some examples that you would see in nature, hopefully, if you go outside, right, on a dewy morning. Okay, so droplets of dew nucleating on a spider's web, right? Or if you in fact take showers in the morning or afternoon, evening, you might see condensation on your shower screen. Yeah, steamy conditions, reach saturation point equals condensation. Okay, so we have something that nucleates on that glassy surface or on our silk surface of the spider web and then grows to a droplet. What have we got here? Some of you might have seen this experiment on YouTube. It's kids. I chose this one because it has been okay, we can only handle so much banjo. Now, so what happened there? What happened? So, by changing the pressure within the vessel, okay, we've got some water in there obviously, changing the pressure, okay, we're reducing the vapor pressure and the surface tension on the surface of that water, it should start to vaporize, right? But to vaporize the gas, sometimes it's going to need some kind of nucleation point, okay, or tiny droplets, right? The gas will go out of the atmosphere, and when you put something in there, an impurity, okay, such as dust or smoke, into that atmosphere, okay, as we change that pressure, the vapor, the water vapor, can then nucleate molecules of
minutes.
impurities.
I have to do
Okay,
this.
so that's why when the smoke was in the chamber, right, we changed the vapor, the pressure in the chamber, we actually got nucleation and growth to an extent on those impurity particles, which appears as a cloud. Right? So that's condensation, nucleation and growth. Okay, so another form of nucleation and growth, okay, evaporation or vaporization. Okay. The two are different. Okay, so what's vaporization? Vaporization, we're essentially bringing the entire body of material to its vapor point, okay, or boiling temperature. Alright? So that's essentially boiling. Evaporation is not. Evaporation is occurring at the surface. Okay? Most of this interaction is occurring at the temperature of the body, could be room temperature, okay, something like that. Alright? And we're just approaching steady state equilibrium over time by drawing molecules from that body. Okay, so they're a little bit different. Another one people forget about, cavitation. Okay? Cavitation is a massive engineering problem. Right? Typically, defence organisations around the world spend millions of dollars on solving cavitation issues. Okay? What is cavitation? So this is the change of the physical state of matter from the liquid phase into the gaseous phase due to an acute pressure drop or shear at a surface. Okay? So if we've got our impeller of a ship or a submarine spinning at a certain rate, right? At the surface between the water and that propeller, there's a shear force, usually. All right. And associated with that motion, there's also a pressure drop. Okay? An instantaneous vacuum can occur between those two surfaces, between the liquid and the solid surface as we're moving. So what happens? The water will essentially boil locally at a point on that impeller, forming a gas bubble. And that's what you can see there. Okay? These spiral gas bubbles formed by cavitation process. Right? Now, it doesn't appear to be a huge problem, but what happens is, in actual service, that gas bubble pops. And every time a gas bubble pops, it imposes a force, okay, on the impeller, and that causes erosion. Okay? So cavitation actually leads to erosion on rotating components, particularly in marine environments. Okay? And the material will gradually erode away. So it's a big problem, and trying to change designs of our propellers and impellers to minimise or limit cavitation, okay, is a big engineering problem. Another example of nucleation and growth, effervescence. Yeah? So what's effervescence? What's the chemical reaction that's going on there? It's not such a reaction, this is a solubility limit. So typically effervescence in soft drink, in alcoholic beverages are dissolved carbon dioxide. Yeah? When our pressure conditions change, i.e. we open up our bottle of soft drink, we pop the cork on our champagne, pressure changes, equilibrium changes, the dissolved carbon dioxide nucleates at a point, grows into a gas bubble out of the liquid, and rises to the surface. Yeah? Who here is into fine dining? Anyone? Not many students can afford it. So, I don't know, if you watch a lot of old movies and things, you see a lot of bartenders behind a bar, American films, polishing up the glasses and the glassware in a fancy restaurant or something like that. Yeah? So, it used to be a little bit of a thing, old times. If you pour your champagne into a glass and you get bubbles forming anywhere on the glass other than the bottom of the flute, that glass is dirty. Yeah? So your rich clientele will say, Garçon, yeah, this glass is dirty, take it back. I'm not drinking that. Alright? So this is actually the thing behind our bartenders polishing the crap out of their glassware. Okay? smooth, if it wasn't clean, you could see the nucleation and growth of a bubble on the side of our glass, all right, rather than at the bottom of the flute. Okay, so the actual shape of champagne glass, yeah.
Does that mean also if you had like little scratches or fusions that?
Oh, I don't have video. That's why the a champagne flute is designed the way it is. So at the very, very bottom of the flute, it's a very particular angle. That angle actually allows for the nucleation and growth of effervescence at a single point. So typically when you pour your champagne, the bubbles should be coming from the center of the glass. But as we've started to mention here, we can get it to work in both ways as well.
Probably the single most important beverage in full-service restaurants is beer. With a per capita consumption of 20.6 gallons, the U.S. is one of the largest volume consumers of beer in the world. And to a restaurant operator, that means a significant amount of traffic and, in turn, a significant amount of profit. That's why our glassware engineers have conducted extensive research to develop the best glass for presenting and serving beer. And we are proud to introduce performance nucleation technology. Our engineers have developed a new technique of etching that encourages the creation of bubbles in your beer. This technology enhances the experience for the consumer and makes for a much more impressive presentation. Here's how performance nucleation technology works. On the left, we have a standard pint glass. On the right, we are using the Nonic glass, part of Cardinal's line of nucleated glasses. The nucleation sites are created through controlled breaks in the smoothness and texture on the bottom of a glass. This technique makes for a much more appealing beverage by promoting head retention for visual appeal, as well as an enhanced aroma for the constant flow of carbon dioxide bubbles. This adds up to a presentation and taste that will help keep the patron coming back. Cardinal has developed a product that is appealing to bar owners and operators and their patrons, while easing the conversion for operators who are already using Cardinal beer glasses. By keeping the same item numbers and the same pricing, we've made it simple, easy, and irresistible. We offer shapes that enhance numerous styles of beer. Nonic is our fully tempered and stackable line that's perfect for a fast-paced bar atmosphere because it is 5 times stronger than annealed glass. The unique shaped tulips are used for local ales and lagers and are designed for lower carbonation brews with a shape that contains the head for a better tableside presentation. When it comes to nucleation, Cardinal is viewed as the experts. We've been perfecting and supplying nucleation technology for over 10 years in beer, champagne, and sparkling wine glasses. For more information about the products mentioned in this video or other Cardinal International product.
Okay, so the science of beer again, yeah. Okay, so you saw what happened there in terms of nucleation and growth. Okay, so essentially this company here is taking common beer glass, making it a little bit more complicated than it probably needs to be, etching a specific pattern, scientifically engineered pattern on the bottom of the glass to enhance the nucleation and growth kinetics of carbon dioxide coming from the beer. Okay, to provide nice head and aroma type characteristics and things like that, and better presentation. All right. So hopefully you can now appreciate, okay, nucleation and growth, even when you're at the bar, away from university or whatever else. Okay. All right. Now, this slide is a very famous slide in this course. So Professor Nagy Valinor introduced the Mentos Diet Coke reaction into the exam paper several years ago, and he implored that I keep it in the course. So just based on his wishes, here we have our Mentos Diet Coke slide. All right. Is everybody aware of the Mentos Diet Coke reaction? Yeah. Does anyone care to explain it to me? What do you do? What happens? Hmm? Yeah. Yeah. Very fast reaction rate kinetics. Yeah, that's right. That's right. Pretty straightforward. Okay. Basically, we've got on the surface of the Mentos, okay, we've got very, very fine features that assist in the nucleation and growth of carbon dioxide coming out of saturation in the Coke. All right. What happens when they're present? Okay, we get the rapid evolution of carbon dioxide out of here. All right. Which imposes a little bit of force and things coming out of the bottle. Now, does anybody actually try this experiment using just regular Coca-Cola, Pepsi, and the diet product? Anyone compare the two? No? So in Diet Coke, we've got a few other lovely chemicals in there, right? For sweeteners and things. Aspartame is the one that actually also reacts as a slight catalyst for the reaction. Okay, so if you're trying this at home, and I'm not telling you to, Diet Coke will go a little bit better because we do have extra catalysts in that system. Yeah? Here it is explained more scientifically.
Matty Todd asked us to do a video on
picked this
Coke
one
and
for the
Mentos.
accent.
Luckily for her, Science Nation is here with an explanation.
The surface of a Mento has hundreds of thousands of tiny imperfections. These imperfections allow CO2 to form bubbles, and that process is known as nucleation. These bubbles quickly build up and gush out.
Certain chemicals in the liquid accelerate the process. Diet Coke is especially good as it contains aspartame and potassium benzoate. Using our patented Science Nation Mentos dispenser, we can release 4 Mentos at once.
George, let's go.
Okay. So, again, hopefully, appreciation now for what type of nucleation event would that be? Heterogeneous, yeah? Localized nucleation at a very specific site where the activation energy for nucleation is lowered. And obviously it's lowered quite dramatically by that surface for that reaction to occur so quickly. Okay. So, as promised, we've also got a few examples again from nature. Right. In melting. Okay. This is also a nucleation and growth type process. Okay. So the transition from solid to liquid often nucleates at a free surface or an interface heterogeneously first. Okay. Due to the presence of either impurities, surface faults, or increased structural energy. Right. So what I've got here as an example, this is a photo. So this is lake ice, okay? In nature, surface of a lake, frozen over during winter. Spring comes along, temperature goes up, things start to melt. All right, but what we have here is essentially a grain boundary in that ice. And we can see very, very clearly that along this grain boundary, either side of it, we are getting the nucleation of liquid. Okay? Subsurface or at the surface of the ice. Mm-hmm. So, why would it occur at a grain boundary preferentially to anywhere else in the structure of our ice crystal? The diagram that's up there might help you a little bit. Yeah, so again, it's all about local energy. Oh, there was a hand. Okay, tell me.
Well, at the grain boundaries, less water, so there'll be a lower activation energy to break the
Yep. So that's basically it. So grains are ordered crystallographic lattice. Yeah. A grain of material. Okay. In the bulk material, there's many different, many grains. Okay. They're all essentially of different orientations, typically. So at the grain boundary, we lose that periodicity, okay? And the atoms that seem to be here in our grain boundaries are just doing as best they can to bridge that gap and still bond the material together. Grain boundaries are often the place of weakness in a material. Right? To actually have this structure costs the material a lot of structural energy. All right? So if we've got an increased site of energy here, okay, best way, well, basically that can be enough to overcome the activation energy for nucleation to occur. So that localized point here, and you can probably envisage this structure is actually closer to the structure of water or something like that, of the liquid already. It's not ordered, okay? It's not crystalline lattice. So this is typically the favoured point for nucleation to start. And we see it in our metals and things as well. At grain boundaries, this is where often our precipitates will occur, right? Or melting will start, typically at a triple point, all right? So what have we got here? We've got some videos. Oh, okay. All right. Freeze. Freeze, freeze. All right. So what we have here, does anybody know what this might be? We did maths 2003. Electron microscopy. This is a TEM image of solid. Okay, it's actually a colloidal crystal setup. Alright, so what we're seeing here are atoms, okay, or columns of atoms. Okay, we can see hopefully there is periodic array here. This is in a lattice. Yep, in solid state. What we're doing to this material is heating it up very close to its liquid temperature. Okay, it wants to melt. What we can see as we heat it up, you can see localized areas like this appearing and disappearing stochastically, randomly in the material. I'll just pause. So that structure there is essentially amorphous. It's liquid. Okay? In terms of translation, about 30 atoms in size, radius. Alright? So what the material is doing in random places throughout the crystal, these structures are forming. The energy there is locally favourable for things to try to start to melt. Right? However, you can see something of this size is appearing and then disappearing. Okay? It hasn't quite overcome the energy barrier required for it to grow and melt.
So is this all just one crystal?
That's
Okay, and then in the whole image there are any green boundaries?
no, just this is a single crystal sample. Yeah, and we're looking at the center of a thin foil in a TEM. Okay. Okay. And disappears. And what we've got here is the modelling. I'll just hit pause. Where we've got two nucleation points in close proximity to one another. Right? What happens is, because they are in close proximity to one another, hopefully, possibly, what's going to happen here is we're going to exceed the critical size or radius for nucleation to move forward and growth to occur of this phase. All right. So here we see them join. Okay, and beyond this point, we can start to see instabilities occurring around here and here. And this phase would essentially start to grow as liquid. All right. All right. So hopefully that is a very good example on the atomic scale of how this homogeneous nucleation and growth occurs when we're changing from one state to the next. I think this is the same one here. I'll just double check. I think this is the same work. can see our 2 points here where we're melting locally. They combine and would essentially, once they hit that critical size, very quickly grow and essentially have the material melt. Okay. Crystallization is also very simple. So what's crystallization essentially? It's probably the true meaning of solidification. We're going from the liquid state to the solid state. By definition, solid state is typically crystalline. Right? So the formation of a crystalline solid from a liquid or from an amorphous state. So a vitreous solid can also crystallize. Window glass can crystallize, for example. Okay. So we can do this from using ionic solids. So hopefully in science, high school science, somewhere down the line, you've gone and crystallized copper sulfate, typically on a piece of string or a wire. Yeah? So what's going on in that event? What's the piece of string acting as? Yeah, it's a heterogeneous nucleation site in the middle of our fluid. It's also a little bit of a conductor of fluid up and down the string. Okay. So different types of crystallization, we can get them from covalent solids, things like diamond, silicates, borides, metal oxides, halides, molecular solids like water. Okay. We can even get it in polymers. Crystallization, where our polymer chains line up. Right? And probably the most typical example are metallic solids, and there's just an example of bismuth crystals and how they prefer to grow. Okay. So we've got a few examples here. All right. Let's have a look at heterogeneous nucleation. Some of these are better than others. Oh, yeah. Okay, so here we have a liquid on a cooled, doesn't look particularly clean, but a cooled, clean substrate. Okay, we can see them crystallize. When we add an inoculant or an impurity, as soon as it touches it, they essentially crystallize. Now this is called supercooling. This one here is particularly stable. Okay, so essentially, I'll just turn that off. With this experiment, we've got our water droplets on a cooled stage. Okay. The stage is continuously cooled, right, to lower temperatures below the freezing point of water or whatever the liquid was. Okay. And we saw there a couple of those droplets solidify, crystallize very quickly. And that could have been because those droplets had an impurity, or the surface below them had a scratch or something in it that acted as an inoculation point, or that could have been true homogeneous nucleation. Okay. But then we saw when our experimentalists dropped, it looked like pepper, onto those particles, okay, that powder, whatever it was, acted as a nucleation site for crystallization. Okay, and instantaneously, as soon as that pepper or whatever it was hit it, it's crystallized. Okay, and that's our example of heterogeneous nucleation. All right. systems like to add on to a plane, a crystallographic plane, where the energy is also the lowest. Okay? And they'll grow preferentially on that plane. Okay, I don't know if we'll go over the copper sulfate one. I think that's, we're going okay for time.
Just like these spills, Ajax.
Have you seen crystals of salts? Crystals are made through a process of crystallization. Let us try to make salt crystals from a solution of salt. For this we need thread, a saturated solution of copper sulfate, and copper sulfate. First we will make a supersaturated solution of copper sulfate.
So that's important, supersaturated.
Light the spirit lamp, place the copper sulfate solution on the burner, heat the mixture. Now keep on adding copper sulfate till no more salt is dissolved. Fasten a thread on a support and suspend it in an empty glass. This thread will act as a nucleation center in the container. Now remove the solution from the burner. Pour the solution in the glass. Leave the glass aside for a few days. We see salt crystals formed on the string. This happens because the solubility of salt in water increases with temperature of solution. So more salt gets accommodated in the solution than it would have if water was at room temperature. This solution is called a supersaturated solution. The salt from this supersaturated solution gets precipitated out when the solution returns to room temperature. The salt molecules that get precipitated out start forming crystals at the nucleation center, which is the thread in this case. Crystallization is the process of formation of solid crystals of a substance in this case. Crystallization.
Come here. Alright. So obviously the string is a good nucleation site for the crystals to form. You can also notice there's a couple there on the bottom. If this system didn't have a piece of string and our container was not a viable nucleation site, what would happen here in this case? Yeah, homogeneous nucleation. We will probably get nucleation occurring within the body of the solution, randomly or stochastically. What happens though, as this starts to fall out of solution, these initial precipitants would drop to the bottom. Okay? The crystal is typically got a higher density than the liquid. Right? And those crystals can then act as nucleation points for further growth. So on the bottom of the container, this is probably what's happened to an extent. Right? So we've had some come out homogeneously from solution, drop out of solution to the base, and then act as a nucleation site for further growth. There'd also be a little bit of a temperature gradient initially in this system, creating a little bit of stirring and things. But that can also, a temperature gradient can also distribute our saturation gradient within our body there. Okay? So sometimes the bottom would be richer in nucleants anyways. Okay? Because they are denser, they will fall to the bottom. All right. Oh, last one.
At AHM, we like to keep things simple. So we've created Noctober, a month where you can stop doing stuff.
Okay. So this is bismuth.
In this video, I'll be showing how to take ingots of solid bismuth, which can be purchased online, and use them to form these complex crystals on a kitchen stove. Bismuth has a melting point of 520 degrees Fahrenheit, which for a metal is very low. It's still more than hot enough to cause burns, so for this project, safety goggles and leather gloves are essential. This is 5 pounds of bismuth metal in the form it's usually sold. the first step in the process will be to melt this down. A small stainless steel saucepan makes for a good crucible. I suggest using a pan you're not attached to, because it will likely never be clean again.
Again, talk to your mum.
Once
first.
fully liquid, the heat is turned off. It will take quite a while to cool. In the meantime, all the oxides and other contaminants.
I'm just going to pause here for a second. So we've melted a liquid here, and you can see what I call a decent scale on top, an oxide scale. Typically when a metal reacts with an oxide, the oxide that forms is going to be lighter than the metal itself. So it will always float to the top. Right? That's important as we move through the video.
Contaminants will float to the top, where they can be skimmed off. As the temperature again falls below bismuth's freezing point, crystals begin forming at the surface, growing downward into the molten metal beneath.
Okay, now I've just told you from the copper sulfate example, crystals are usually more dense than the liquid metal, yeah? It does depend a little bit on the structure of the crystal, as during the case. Here we're getting crystals forming on the surface. Can anyone think why we might be getting crystals forming on the surface rather than on the bottom of our saucepan? It's probably going to be hotter there as well. Oh, yeah, maybe. Got a little bit of air cooling. Anyone think of two reasons? Yeah? So bismuth, I think they're about the same, the bismuth. I think the crystal should theoretically sink, okay? But it's got a whole bunch of allotropes and things in there as well. There's some weird tetragonal structure of bismuth. So the atoms aren't necessarily packing so greatly. So I think their densities are very, very close together, but I still think the crystal is slightly more dense and should sink. Can I think of any other reasons? Yeah?
If you don't kind of scrape off that oxide layer properly, you have little oxides at the top, and that would be the nucleation side.
Yep. So that's one reason. We've got oxide impurities floating on the surface which act as a nucleation site to start with. What's another one there? The last one's just the temperature gradient. Okay? So at the surface there we're air cooled. Okay? Whereas from the hot plate we're heating from the base, okay, and then around the outside of our saucepan. So we've actually got slightly hotter around the edges. Right? So just based on those two things, the inoculation at the surface plus the temperature gradient, we're actually getting crystals forming on top and growing down into our melt.
We can gently move the crystals as they grow to be sure they don't freeze to the bottom of the pan. The moment they can be felt contacting other things below the surface, it's time to pull them out and see our result. At first, the crystals appear only silver, but a layer of oxidation quickly adds color, the shade of which is determined by what temperature the crystals are when they first contact the air. We only get one chance per cooling cycle to create crystals we're interested in, but if the results aren't satisfying, it only takes a few minutes to melt everything down and try again. A synthetic bismuth geode is also possible to create using a small ceramic bowl as a mold. The ceramic needs to be preheated so it doesn't crack from temperature shock when the bismuth is poured in. This particular process has a high potential for spills, so it's much more dangerous than making surface layer crystals with the previous method. Don't try this one at home. I wait for the metal to begin cooling, taking off the top layer so it doesn't seal completely closed. Shortly after, the remaining liquid is poured out of the center to reveal the result. The crystallization can be revealed further by cutting the top portion off entirely. I did this with a hacksaw. If you enjoyed this project,
I'll just pull it up there. You'll also notice the ones that were grown from the surface and the ones that were grown from the base of the ceramic bowl. Just how shapely they are. Okay, these have got 90-degree growth directions. We'll get on to growth shortly, but like I said, certain atoms like to attach themselves to a developing nucleus or crystal as it's growing on certain crystallographic planes or orientations because the energy to attach to that point is lower based on the distance between the atoms. Okay. Okay. Something else we're going to talk about, we've got 15 minutes to go, is inoculation. All right, so we've brought it up a little bit earlier. But what inoculation is this premature formation of a specific crystalline phase from the melt due to its association with a secondary particle or interface. Okay, so this is heterogeneous nucleation, and we're doing it on purpose. Right? One of the best examples in industry is the inoculation of aluminium alloys. Right, so what we've got here are a couple of examples of an aluminium alloy. Right? And we've added the inoculant crystal titanium diboride. Okay? It's typically used in industry to inoculate aluminium alloys. And we're varying the volume fraction of titanium diboride in this melt. So in the absence of titanium diboride, okay, here's our etched microstructure of our sample. So what we can see here around the outside are these columnar grains growing in. Why are they there? Two reasons. They're probably being inoculated from the surface of our vessel we've cast our sample into, plus the edge of the vessel is going to be cooler. So grains will grow inwards to the centre. But then we've essentially got these equiax grains in the centre. Some of them have slight dendritic structures. Oops, backwards. Okay, but they're generally an equiax grain. So they're nucleated in almost a homogeneous way, okay, away from the outer skin of our casting as it's cooling. Okay. However, when we add the inoculant, we can see straight away a dramatic change in the microstructure. All right, we've got multiple tiny equiax grains. Okay. In terms of mechanical performance, what does the smaller grain size mean? Higher strength. Yeah. What does a non-directional orientation of a grain mean? Yeah. So we've got isotropy, okay, rather than a casting texture. All right. And as we increase the volume fraction of titanium diboride, this grain size gets smaller again. We're essentially providing multiple tiny nucleation sites for multiple grains to grow very, very quickly. So that's why they're not growing big. They're being impinged on other little grains that are growing at the same time, being inoculated from those titanium diboride particles. Some other examples, okay, again of crystallization and precipitation. This very, very important reaction in metallurgy. If you haven't gathered already or didn't know, I'm a metallurgist, so a lot of the examples are coming from here. Okay, here we have what are called the starts of our ADA phase, or our GP zones, in a hardenable aluminium alloy. Okay, durality 2024 aluminium alloys, something like that. What we notice straight away is there is a large concentration and an orientation relationship between the grain boundaries and these particles. Yeah. So again, this is similar to that example that we saw with ice, but in reverse. Okay. At the grain boundaries, okay, the structural energy is higher. Okay. And this can act as a nucleation site, or favourable nucleation site, for a new phase to form. That's what's going on here. Okay. Our new phase that's dropping out of solution in the same way that the copper sulfate crystals were dropping out of solution as temperature was lowered. Okay. They're then forming at the grain boundaries. It's also a little bit higher mobility or higher diffusion coefficient at the grain boundaries because of that random crystal structure. Okay. So this one's really important for the strengthening of aluminium alloys. We need these precipitates to give us the strength. All right. What we have to do is homogenise this structure, get them away from the grain boundaries. We do that through heat treatments and cold working to redistribute them more evenly. All right. We've also got examples of nucleation and growth happening from amorphous phases. Okay? So I've told you that solidification really only applies to crystallization. Okay? If we supercool a liquid and it doesn't form a crystal, it's actually called a vitreous solid. It's a little bit different. The vitreous solids are metastable. Right? They're always going to be metastable and want to crystallize eventually because the crystal is the lowest energy structure. Okay, so one of my fields of research is metallic glasses, amorphous metals. Right? We cool them quickly, they don't have time to crystallize. Right? But if we heat them up slowly to beyond their glass transition temperature, okay, so plastics, thermoplastics, metallic glasses, ceramic glasses all have a glass transition temperature. If you heat above that glass transition temperature for a long enough period of time, that material will also crystallise. This crystallisation is going to be probably homogeneous. Okay? It's happening very, very slowly in a very viscous supercooled liquid. All right, so we can see here homogeneous nucleation and growth of crystals in a vitreous metal. All right. Polymers are a little bit different. Those chains have to realign themselves and things like that. Okay, I don't know if we've got time to actually cover this particular slide in detail. We might have to continue it into the next lecture. All right. We've got a lot of examples here of recrystallised aluminium. Okay, so another example of nucleation and growth is recrystallisation. So we've got a solid material. Yeah, we've deformed it. What happens when we deform a metal? What do we induce in the metal structure? Do we know? Maybe it's a third-year subject. Dislocations, imperfections, vacancies. All right. When we deform a metal, we cold work it. Okay, we cold roll it, hot roll it. Okay, we start to deform those crystals. We create defects in the crystal structure in the form of dislocations or vacancies. These dislocations and vacancies are high energy. We're destroying that crystal structure, which is the lowest structure of the material. All right. By inducing these defects, we're increasing the structural energy. They then become sites. If we get enough dislocations and imperfections in our crystal, they then become sites for new crystals to form locally from that site. We will have a big lecture set on recrystallization in week 9, I think it is. All right. So that's something that we can also think about for our recrystallization. So what I'll do, I'll finish up because the lectures stop at 5:02. We'll just have a quick look at recrystallization in rolled aluminium. I think this one's under a microscope, just to give you a feel for it. Okay, let me see here. I'll just hit pause. Okay. So what we have here, again, under a microscope, in our SEM microscope, we can use heated stages. Okay, for recrystallization to occur after deformation, we need energy, we need heat to get those atoms moving again. Right, so what you can actually see in this image here, probably a little bit poorly, we see directionality going across like this. That's our rolling direction. So our material is being squashed in this manner from going through rollers repeatedly. Okay, we've got some very, very fine, tiny little grains. We can't really resolve them in this image because they're very tiny. All right. As we apply heat to our sample, we can see straight away we've got grains starting to grow. They're nucleating and growing. And they usually nucleate and grow from interstices in our grain boundaries. Okay. So this is recrystallization. So a solid essentially transforming into itself. There's no phase change here. Okay? We're not a change of phase or state. We're just going from one energy state to a lower energy state. So here it's fine-grained, highly deformed material transforming into lower energy, large crystals.
This is a Dalarna University production.
This film will give you as a...
All right. We'll finish up there and we'll pick up on Thursday. Okay, so we're timetabled for Thursdays, Mondays and Thursdays. All right, we don't have that Wednesday class in the middle. Thank you.
For heterogeneous and homogeneous nucleation, is there one that's like kind of faster than the other, or does it depend on the material?
It depends on the material. You might be more referring to the growth stages. Heterogeneous will occur more quickly, particularly if there's a lot of inoculants. It depends on the number of sites for nucleation to occur. and how much lower that energy barrier is compared to what the case would be in homogeneous nucleation.
Okay.
So if you've got that A now, if you've got 1 billion nucleation sites that are lower energy sites for nucleation, that's going to happen much more quickly and probably at a lower or undercooling than it would in the case of homogeneous nucleation. So it depends how close the energy is to that tipping point for homogeneous versus heterogeneous, and then how many active sites there are.
Okay, thank you.
Yep.